Hello everyone, Amir with Alizadeh Engineering. We did this transit priority measure study for the city of Edmonton in 2019. So basically, giving you an overview, this is where the existing LRT lines in the city of Edmonton are aligned, and the red dotted line is where we were looking at a shuttle service, a transit service between the existing LRT station, a transit station on the south end of one of the lines, connecting it to an under construction park and ride facility. Basically, the city of Edmonton is expanding towards south and west. And the purpose for this project is as a city lease for a transit center. And let me see if I can bring up this laser pointer. So a city lease for this park and ride facility here at the LRT station is terminating, and the city is building this new facility to the south of the ring road. So we looked at a shuttle service being run between these two, basically connecting this park and ride to the LRT station. This is like a total of 11.5 kilometers. I had to use Google to know how many miles that would be. It goes through 14 signalized intersections. It's a mix of urban and highway ramp intersections. Basically, these two are highway ramp intersections. There is a 5-minute headway considered for this shuttle service at the peak hour. And the goal of the project is to keep the travel time, the round trip travel time, to 30 minutes or under. So the northbound route for this is going through the ring road, through this arterial, and then for the southbound, the blue line, it goes all the way south and then through this arterial back to the facility. So an overview of transit priority measures, they could basically be categorized into 3 categories: regulatory measures, transit signal priorities, and physical measures. A high-level feasibility study was done, basically looking at what are the potential time savings, the maximum potential time savings for this loop service. We looked more into details of that. So basically, our project work consisted of an evaluation framework where we were looking at travel time savings compared to a do-nothing scenario. There was another aspect for the evaluation being the reliability of the service, and that was defined basically as an 85th percentile of travel times meeting the goal of 30 minutes. So versus the average travel time, this is kind of the level of the reliability of the service that was set. We looked at the off-corridor impacts in terms of delays being applied to side streets as a consequence of the changes we are making to the network. And we had an initial screening phase where we used synchro and manual calculations in order to screen out some of the ideas that were basically brought up in a brainstorming and from different stakeholders. So for our model building, what we had was an already calibrated 2017 model that was put together for LRT, and that basically consisted of about the northern section of the area we were looking at. So we took that model. One of the specifics of that model was the modified desired and maximum acceleration functions. This was based on IT's traffic engineering handbook parameters. I will touch on this later. For the traffic data, what we had was traffic counts from 2016 to 2018. For the most part, there were 2017 counts. We got the existing signal timing plans, and we had a travel time survey that was done in 2017. So basically, we took that 2017 model, we expanded it, and we recalibrated that with a travel time survey that we had. Transit priority measures that we looked at for this project included active transit priority, QJumps, bus-only lanes, additional far side lanes, and we also had an assessment of the transit center, the existing one. We looked at signal timing optimizations, and we also looked at bus stop locations or relocations. So the way we did it for the active transit priority is basically we went into the RBC files, and we had set kind of a set of rules for ourselves, and in the sense of how much of the side street splits we are willing to give to the transit in terms of early and extended greens. So this was done to the timing plans, and to know about active transit priorities is that these can basically potentially disrupt the coordination between the signals, and it takes time for the controllers to get back to coordination. And they add delay to the side streets as an effect. For the QJump, in their simplest way, there is basically a reconfiguration of the pork chop, the island. So you are basically connecting the right turn lane to an additional lane at the intersection, and you are given priority to the transit to kind of go before the parallel traffic with a transit signal. An advanced green that you're giving to your transit. So this requires minimum construction, and one of the downsides is that if the buses do not get to the QJump at the beginning of the green, and basically they can't use their signal, they might be kind of entrapped, because then they are trying to get back, merge back into the main road, whereas the platoon of traffic will make it not easy for that maneuver. Another QJump configuration could be basically an extension of the right turn bay, and in this case, the buses get a better chance to use the QJump where the right turn volumes are higher, and they might be blocked by right turners. This needs additional right of way and construction. We looked at bus only lanes at different sections of the road where the slower moving traffic was present. One of the characteristics of bus-only lanes is if they are to be extended through intersections, then you have the conflict of right turners that are crossing your bus-only lane in order to do their right turn movement. Also, it requires provisions for separating buses from the general purpose traffic, and it will certainly work more effectively if you provide bus bays, so that the buses stopping at their stop are kind of out of the way, and it provides smoother and faster travel for the ones that do not want to stop at that certain bus stop. addition of far side lanes are another geometric changes that we looked at, and basically transit can use these with a shared green light. So what you will have with an additional far side lane is you're basically building this section of the road and moving the transit out of the way. The general purpose traffic can also benefit from this because it doesn't get blocked by transit, and these can also work as an acceleration lane, making it easier for the transit to merge back into the traffic. We looked at an assessment of a transit center to the north part of the route as well. So for that, using Vissim, we were able, because we had all the information of the existing lines using the transit center, we were able to assess this, basically looking at what would be the optimal location for the shuttle service, being along the arterial or inside the transit center, and what are the impacts of the circulation on circulation times, as well as we looked at this intersection, the egress, and how a preemption or a transit signal priority would affect the operations of this intersection. We used Synchro for our signal timing optimization. We didn't know that Alex is working on that web service. It's not out yet, but so this is a painful process where you have to do your signal optimization in a separate tool, and then it's an iteration between the two. We used Synchro as our tool because basically in our screening stage, we had a Synchro file built, and we used that for screening of some of the measures we were looking at. So basically, and we also looked at relocation of some of the bus stops. We looked at a different combination of these priority measures at different locations. We evaluated these through extensive running of the models. And basically what we ended up doing was considering the fact that this project, the extension of LRT line is going to be happening in sometime in the future, not known, and the implementability of these measures to be as quick as possible. We try to focus on active signal measures rather than geometric changes, as they are more faster applicable. So basically we had a base scenario, a do nothing scenario. In our first scenario for testing, we only included active signal measures, and we also developed a hybrid scenario that had the signal timing optimizations that we looked at, active signals, same as the previous scenario, and some limited geometry changes, basically focused at two locations, two most busier intersections at the northern part of the area we're looking at. And as a recommendation for future, we added an auxiliary lane. So this is a summary of how these final tested scenarios look like. So if you look at here, the average travel times during the AM and PM peak versus the 85th percentile being a representative of the reliability of the system. As you see, the AM peak is the target of 30 minutes is always met, and system is also reliable at 85%, being travel times on, less than 30 minutes. With a PM peak, what we see is that the base scenario at 2020, even the average travel times are going to be over 30 minutes. With the active signal scenario, that 30-minute will be met, but the system is not reliable to the desired level. And with a hybrid scenario, we were able to bring it down to less than the 30 minutes. I want to get to the challenges and findings that we had through this project, and basically this is after that context, this is what I would like to share with you and probably get a feedback. This is how we did this, and there might be different ways of doing it. So as for the QJumps, we were using static routes where setting up the QJumps. The problem with using the static routes is that you're basically fixing that route, telling your transit to always use the QJump, whereas that's not the case in the field, where you have a driver of a transit basically having an evaluation of the conditions and deciding between taking the QJump or staying on the main road. So to overcome that limitation, we used partial PT routes. And with that, we combined it with a formula to basically mimic the driver's behavior. We introduced two parameters to this formula. That was the status of the signal and also the length of the queues. So if the driver sees the signal being green or the queues being short, he might stay on the main road, but on the other hand, they might take the QJump. Another challenge that we had was we started with using this geometry as suggested by PTV in the transit examples. This is basically a separate connector connecting that QJump link back to the main road. What we saw with our simulations was that as congestion happens downstream of this connector, and with lack of any conflict rules or priority rules downstream, this is the case that could happen sometimes. So what we ended up doing, we opted for a different geometry. This is what we use in freeways when a lane drop happens. So basically this is, for this example, this is going from a 3-lane link to a 2-lane link. Basically to a 3-lane link that has one of the lanes set as close to 0 width. So the connector itself in this case will take care of the merging maneuver rather than us trying to tweak the priority rules and have a combination of those. We also looked at active signals and QJumps as a comparison between these. So our finding was where the turn-based lengths are shorter than average queues, buses could be, like if the queues on the main road are longer than the turn bay, buses could be not able to get to the QJump and effectively use it. So in these cases, active signals can perform better versus the QJumps. But this obviously comes at the expense of longer delays to the side streets because you're giving a bigger chunk of green time to your transit and taking it away from the side streets. QJumps can do better if these there are shorter queues and basically they have lower impacts on the side streets. There was an expectation of if we combine these two measures together, we would probably get better results. But what we saw in our simulations was that if you combine the active signal and the QJumps together at one location, what happens is that entrapment of transit in the QJump can basically last longer because you're giving that the transit is approaching the intersection, basically activating the the active signal, extending that green, and then if they choose to pick the QJump, they would be entrapped here for a longer time. So that's not recommended. And also the adverse effect of QJumps with far side bus stops. This is something that we also learned through our simulation. Is basically when you are doing a QJump, you are letting the transit to kind of bypass the queue and be ahead of the queues when the signal goes green. But if you combine it with a far side bus stop, you are basically letting the transit block one of the lanes, and this is a harder maneuver for the general purpose vehicles being stopped here trying to change lane into the adjacent lane. Other findings, and I'm going to wrap this up with these 3 points, is that so our general finding is that the combined effectiveness of the measures is not always the sum of them all. So simulation really helped us in evaluating the effects. Something to keep in mind is that the effect of additional lanes. So basically when you're making a geometry change, such as a QJump or an additional lane, you got to keep in mind that by this we are increasing the crossing distances for pedestrians and also the clearance time for vehicles. So in its own, it's taking away some of the capacity of the intersection by that geometry change. And going back to the modified functions for desired and maximum acceleration, which is kind of carried on from the model that excuse me, we started using. So the model, as I mentioned, was using the ITE parameters. What we figured is that the ITE parameters are a little, I would say, not as expected in terms of how the characteristics of heavy vehicles would be using those parameters. So if you change the default parameters to IT parameters, the speed of the heavy vehicles relative to cars wouldn't be as expected. And on the other side, what Vissim uses as default parameters look to be a little aggressive. So what we ended up doing and we decided to do is, for our next project, we're going to be looking at doing some drone surveys in order to be able to extract that data, the vehicle characteristics, and basically use those parameters in our Vissim model for the next project that we have ongoing. So that wraps up what I had for this project. Hopefully I made it in time. Yeah, and I'm open
for questions. Go for
Sure.
it.
Yeah. So I got a question. I mean, being from Canada, you have access to the Canadian Capacity Guide and things like that. In the early screening process that you were mentioning, especially with intersections with near side, far side bus stops, did you consider using Canadian Capacity Guide for that, because that's built into that kind of that analysis, near side and far side?
No, and no, we didn't look at the Canadian capacity guideline, but so I'm wondering, are there recommendations that you mean by that, like in terms of which type of bus stop to be used, or because we were looking at the existing. To start, we had those bus stops being existing, and we were kind of building on top of that. So.
Well, I mean, within the criteria within the Canadian Capacity Guide, they have different parameters than what's in the HCM set of parameters in that analysis. So it's focused heavily on additional transit parameters, and such parameters are how many. I mean, you still have how many bus interactions do you have, but also it's like, are these near side bus interactions or are these far side bus interactions? And I mean, it could provide some additional screening
Yeah, no, we haven't looked at that.
Yeah, okay.
But thanks for. Yeah, go ahead.
Did you have conversations with the bus operators? I know in recent conversations we've had from the driver's perspective, they prefer staying in the lane as opposed to coming out of the lane, then have to merge back in. And of course, as traffic people were like, no, you need to get out of the lane so my flow can keep going. But did you have any conversations as far as with the operators at all?
Yes, so I went to some of these locations where the queue jumps are, and I talked to some of the drivers themselves. Some of them, probably the same conclusion. They rather stay on the main road than using the queue jump, because it makes it harder for them. The merging back maneuver is something that they try to avoid, and that's with the formula that we added to the model. We were trying to kind of mimic that, for the transit to stay on the main road if they see the conditions are suitable for that. Yeah. Sorry, yeah. Go ahead.
Was there any logic in the signals where if they had a near side station where a detector would sense that the vehicle was still at the station and so that it could approach the signal and get a queue jump? Or was any of that logic coded into the signals? Yeah,
so for the queue jumps, we basically had two detectors. So kind of being able to pick the transit as soon as possible before reaching the intersection. So giving them that if they have picked to be on the queue jump, to pick them as quickly as possible and give them that green. Yeah. Yeah, go ahead.
When you said that QJump lanes in conjunction with active signals, I'm assuming that's active TSP with the green extension, correct?
Correct.
And when you said when those two measures are used in conjunction with each other, there was a delay for incurred by buses using the QJump lane to merge back once they reach the intersection. Is that correct? Is that right?
Not necessarily a delay. I mean, there was an expectation if we combine these two, we might get the effect, the savings of both combined as a sum of these two. But what I said was that in that case, if you combine these, you basically you get your transit calls the extension on early green, getting through that detector, and if they choose to pick the queue jump, in a case that they are in the queue jump and trying to merge back in, because they've already called that extended green, it takes a longer time for the parallel traffic to kind of get the red and stop. So they could be potentially entrapped for a longer time in the queue jump.
Okay, so by entrapped, you mean the buses are at the end of the queue jump ready to merge back in?
Yeah, exactly. And then when you have coordinated signals, you basically have platoons of vehicles going. So that's a harder maneuver for them, that merging back in.
Okay, so I guess my question is, with the check-in, you have separate check-in detectors and check-out detectors for the TSP, correct?
Yeah.
So wouldn't the check-out detector already be at the end of the queue jump lane, and when the bus reaches the end of the queue jump lane, wouldn't that signal the end of the green extension and therefore the end of the green interval, allowing the bus to not be entrapped?
Well, I guess, yeah. Well, you want to have your check-in at the middle of the intersection so that you know that the transit has already left the intersection. If you put it on your queue jump where your link is, you're not sure if the transit has got a chance to clear the intersection. So you're basically giving it a wrong signal about this has already checked out. So you put it in the middle of the intersection, the checkout detector, and that basically ensures you that the transit has already left the intersection.
Oh, okay.
Yeah.
Yeah, because I was wondering if the checkout detector was like still at the intersection, like just past the stop bar. So that way, when the bus first exits the QJump lane, like that could signal to the intersection to end the green, and therefore, like the general traffic will stop. But then the bus, having already entered the intersection, can then be guaranteed to proceed in the next sector.
Yeah, yeah. It's, but I actually haven't looked at it like this, but this is a good idea. Yeah.
Okay, thank you. Let's put our
Thank you.